Welcome to lecture series EPG Padasala for Computer Science. In this lecture, we will be discussing cohesion and coupling. Learning objectives: outline the issues in software design which has an impact on software quality, articulate design principles of cohesion and coupling, outline the different levels of cohesion and coupling. Software architecture. A software architecture enables a software engineer to analyze the effectiveness of the design in meeting its stated requirements. Consider architectural alternatives at a stage when making design changes is still relatively easy. Reduce the risks associated with the construction of the software. Focus is placed on the software component, a program module, an object oriented class, a database, middleware. We follow the divide and conquer principle. We are aware that the deliverable of the analysis phase is a software requirement specification document, which is a legal contract between the client and the developer. The requirements are mapped or translated into a design document. The design document has to be very carefully prepared considering the functional requirements. While preparing the design document, care has to be taken the design is evolvable, which means even after the software has been deployed, any changing requirements can be incorporated in the design. As I mentioned, we follow a divide and conquer principle. Software is divided into modules. Modularity, a concept closely tied to abstraction. Modularity supports independence of models. Modules support abstraction in software, supports hierarchical structuring of programs. Modularity enhances design clarity, eases implementation, reduces cost of testing, debugging and maintenance. Cannot simply chop a program into modules to get modularity. This is one important point. You cannot simply chop a program into modules to get modularity. Need some criteria for decomposition. Effective modular design has a very high impact on the quality of the software product deployed. To present an outline of what modules are, module has an input, process and output. The output of a module can be an input to another module. Modules can be individually tested. Modules can be reused. Desired class or object interaction. Maximize internal interaction, which is cohesion, easier to understand, easier to test. Minimize external interaction, coupling can be used independently, easier to test, easier to replace and easier to understand. A module must have high cohesion and low coupling. Characteristics of good design: component or functional independence, exception identification and handling, fault prevention and fault tolerance. the characteristics of good design, if followed, you will be able to deliver a high quality software product. Functional independence. Functional independence is a key to any good design due to the following reasons: error isolation, scope of reuse, understandability. Functional independence is measured using cohesion and coupling. Cohesion, the degree to which all elements of a component are directed towards a single task. The degree to which all elements directed towards a task are contained in a single component. The degree to which all responsibilities of a single class are related. Types of cohesion: coincidental cohesion, logical cohesion, temporal cohesion, procedural cohesion, communicational cohesion, sequential cohesion, and functional cohesion. We will be discussing each type of cohesion with an example. Coincidental cohesion: parts of the component are unrelated, or to state it in other words, a module is said to have coincidental cohesion if it performs multiple unrelated tasks. Parts of the component are unrelated, unrelated functions, processes, or data. Parts of the component are only related by their location in the source code. Elements needed to achieve some functionality are scattered throughout the system. Coincidental cohesion is the worst form of cohesion. Example for coincidental cohesion: all of the following in one module: logic to produce student list, logic to produce class grade report, logic to check email, logic to change password. That is what I said. A module is said to have coincidental cohesion if it performs multiple unrelated tasks. When I stated the characteristics of module itself, I said a module has an input, process, and output. A module must perform a well defined task. Logical cohesion: elements of component are related logically and not functionally. Several logically related elements are in the same component, and one of the elements is selected by the caller. May include both high and low level actions in the same class. May include unused parameters for certain users. Example for logical cohesion: a component reads input from tape, disk, and network. All the code for these functions are in the same component. Operations are related, but the functions are significantly different. Temporal cohesion: elements of a component are related by timing. Difficult to change because you may have to look at numerous components when a change in a data structure is made. Increases chances of regression fault. Component unlikely to be reusable. Often happens in initialization or shutdown. Example for temporal cohesion: an initialization procedure which does the following: opens all files, initializes arrays and all variables, sets all constants, sets all flags, reads the first transaction. A termination procedure which does the following: writes array contents to disk files, closes all files. Procedural cohesion: elements of a component are related only to ensure a particular order of execution. Actions are still weakly connected and unlikely to be reusable. Changes to the ordering of steps or purpose of steps requires changing the module abstraction. An example for procedural cohesion: a module is said to possess procedural cohesion if the set of functions of the module are all part of a procedure in which certain sequence of steps have to be carried out for achieving an objective. Examples: a function which checks file permissions, then opens the file; the algorithm for decoding a message. Communicational cohesion: module performs a series of actions related by a sequence of steps to be followed by the product, and all actions are performed on the same data. Action based on the ordering of steps on all the same data. Actions are related but still not completely separated. Module cannot be reused. An example for communicational cohesion: update record in database and send it to printer, update a record on a database, print the record, fetch unrelated data at the same time to minimize disk access. Sequential cohesion: methods are together in a class because the output from one part is the input to another part, like an assembly line. The output of one component is an input to another, occurs naturally in functional programming languages. An example for sequential cohesion: functions in one procedure. Search array for a certain name, place the name in another array and sort the array, change the name from last first to first last, print first last name. Functional cohesion: every essential element to a single computation is contained in the component. Every element in the component is essential to the computation. All the statements in the procedure are related in the performance of a single function. Functional cohesion is the strongest form of cohesion. In a functionally bound module, all elements of the module are related to performing a single function. A module is said to possess functional cohesion if it performs exactly one task. Function like compute square root, sort the array are clear examples of functionally cohesive modules. Modules in a quality assured software product must be functionally cohesive. Of course, in practice, to achieve high cohesion, there are bottlenecks. However, the designer and programmer must try to achieve high cohesiveness to the maximum. I would like to state again, in a quality assured software product, modules must be functionally cohesive. In practice, to implement all the modules to be functionally cohesive is difficult. However, the designer and programmer must try to achieve it to the maximum. Coupling: the degree of dependence, such as the amount of interactions among components. You can see in the diagrammatic illustrations given. The first one illustrates components with no dependencies, which is not practical. The second diagram illustrates components that are loosely coupled having some dependencies. The third diagram illustrates components that are highly coupled, many dependencies. A module must have low coupling. High coupling is not preferred. When modules are coupled, the major drawback is ripple effects, which means when a module is modified, the other related modules may have an adverse effect, which means when a module is modified, there may be a necessity to modify the related modules also. High coupling makes modifying parts of the system difficult. Example, modifying a component affects all the components to which the component is connected. The first diagram, which illustrates no dependencies, is not a practical case. Coupling addresses the attribute of degree of interdependence between software units, modules or components. As I have said, lower the better. No coupling, ideal, but as I have mentioned, it is not practical. The types of coupling: data coupling, stamp coupling, control coupling, common coupling and content coupling. Content coupling: a module directly references the content of another module. Component directly modifies another's data. Component modifies another's code. Example, jumps, go to, into the middle of a routine. Example, part of a program handles lookup for customer. When customer not found, component add customer by directly modifying the contents of the data structure containing customer data. Common coupling: more than one component share data such as global data structures. Usually a poor design choice because lack of clear responsibility for the data, reduces readability, difficult to determine all the components that affect a data element, which reduces maintainability, difficult to reuse components, reduce ability to control data access, have to look at many modules to determine the current state of a variable. Side effects require looking at all the code in a function to see if there are any global effects. Changes in one module to the declaration requires changes in all other modules. Identical list of global variables must be declared for module to be reused. Module is exposed to more data than is needed. An example for common coupling: process control component maintains current data about state of operation, gets data from multiple sources, supplies data to multiple sinks. Each source process writes data to global data store. Each sink process reads directly from global data store. Control coupling: component passes control parameters to coupled components, may be either good or bad depending upon situation. Bad if parameters indicate completely different behavior. Good if parameters allow factoring and reuse of functionality. Example for control coupling. Control coupling occurs between modules when data are passed that influence the internal logic of a module. Example, flags and switches. In an example of control coupling, a module that retrieves either a customer name or an address depending on the value of a flag is illustrated. Stamp coupling. Component passes a data structure to another component that does not have access to the entire structure. Requires second component to know how to manipulate the data structure. Example, needs to know about implementation. The second has access to more information that it needs. May be necessary due to efficiency factors. This is a choice made by insightful designer and not lazy programmer. Example for stamp coupling. The print routine of customer billing accepts customer data structure as an argument, parses it and prints the name, address and billing information. Coupling in object oriented design. Three different dimensions of coupling properties may be deduced in object oriented systems, which are interaction coupling, component coupling, inheritance coupling. Interaction coupling methods are coupled by interaction in terms of invocation of each other or sharing of data. Object classes may be interaction coupled. Interaction coupled methods may belong to the same object class. We have to distinguish interaction between different classes from interaction within a single class. Component coupling. The component relationship between classes is defined by the use of a class as domain of some instance variable of another class. In interaction coupling, the focus is on how much information is exchanged between methods and classes. With component coupling, we will analyze how explicit the coupling between classes is. Inheritance coupling. Inheritance coupling only concerns object classes. Two classes are inheritance coupled if one class is a direct or indirect subclass of the other. Inheritance coupling not only exhibit the coupling property between subclasses and superclasses, but also the coupling property between an interaction coupled object class and the inheritance hierarchy. As a concluding remark, what I would like to stress is modules must have high cohesion and low coupling. Only if modules are designed carefully with high cohesion and low coupling, a quality assured software product can be deployed and the maintenance phase is done without any bottlenecks, which means maintenance phase is easier. I acknowledge the authors of the books which I have referred and the web resources I have used for this presentation. Thank you.